Hello everyone. In this session, I want to look at modeling seasonality. In the earlier session, we have looked at how do we actually model the trend in the data, where we looked at linear trend, the quadratic trend, and the exponential trend. Now, some data may have some amount of seasonality in it, right? So in that case, how do I capture that seasonality? Because trend is more about a constant increase or a constant decrease, or increasing at an increasing rate or a decreasing at a decreasing rate or increasing rate. Some such kind of a smooth movement is what is associated with the trend. But in many cases, you see that the patterns wise, there could be some level of seasonality. So if my data is having some amount of seasonality, how do I really capture that as a part of my model? And how do I use that model for forecasting the seasonality for the future? So here I'm going to look at the sources of seasonality, and in case seasonality exists in the data, how do I deal with it? And we have a regression analysis to model the seasonality. And once we have modeled it, how do I really go ahead in terms of developing a forecasted model, forecasts or predictions for the future using this? I'll be using the same data set that I have used for the trend modeling. In fact, I'll use the same spreadsheet where we have completed the trend model. The same spreadsheet I would like to add the seasonality component as well and see if the model can be improved to any extent, right? Now, when we are talking about a seasonal pattern, conceptually it is that pattern that repeats every year. So if the annual repetition is exact, we call it as deterministic seasonality. And if the annual repetition is approximate and has some kind of fluctuations, we call it as stochastic seasonality. But whatever it is, the seasonality arises from linking technology to the calendar, right? Any technology, let's say weather. Weather is the seasonal part because the temperature will be higher in summer, lesser in winter, something like that. So any technology that is involved with the weather, basically the agricultural commodities, right, which are very much related to rainfall, temperature, and various other aspects, they all have seasonal series associated with them. Similarly, preferences can be associated with a calendar, right? I may be interested in travel during summer. More vacation travels may come in summer, or I require the usage of woolen goods in winter. I may not use them during summer. So the preferences change. So even the sales associated with those particular goods where preferences keep changing during the year. So during the start of the schools, the demand for school uniforms, etc., typically rise. So those companies which are manufacturing the school uniforms, the sales for them would be much higher during the school opening seasons, and it could be comparatively lower during the other seasons. Similarly, the relationship between the institutions to a calendar, probably the sales of those companies which are touring companies, which conduct holidays, which conduct tours, holiday tours, etc. For them, the sales could be much higher during the holiday season, but could be much lesser during others. Or those shops which, let's say, even the sales of the cars, right? They may give a lot of offers during the festival season, and the sales during the festival seasons could be much higher compared to the other seasons. So whenever we see that technology is linked to a particular calendar, preferences linked to a calendar, institutions linked to a calendar, weather driven, all these things are very much possible to lead to seasonality in their data. Even in business and economy, we see that every company, you find more and more expansions in the fourth quarter and more contractions in every first quarter. So even that could be something that could be associated with the seasonality per se. Now, if at all seasonality is present in the data, how do I deal with it for my prediction purposes? One way is remove it. So adjust the series by removing the seasonal part in it. First of all, you remove the seasonal part of the data. You adjust the data by identifying the seasonal part and removing it. If the seasonality has not been there, what would have been the typical value? So remove the seasonality part, and after that go ahead and do the trend model for it. And once you have created a trend based forecast, then again readjust it with the seasonality value to do the forecasting, which is very much good when the interest is explicitly on forecasting the non-seasonal fluctuation. I am more interested in forecasting the trend part. So it's better that I remove the seasonal component from the data, look at only the trend part of it, forecast the trend part, and if required, add back the seasonal component to it. So that's one way. And if you look at the business forecasting, seasonal adjustment is not appropriate because I'm interested both in the overall trend as well as the fluctuation seasonally as well. So I'm interested in all kinds of variation. So I need a trend model to be forecasted as well as include the seasonality component also into it. Because in a business forecasting, I'm not looking only at the big picture. I also want the minute level fluctuations that are going to come up. Wherever you find seasonality is responsible for the largest part of the variation, I need to consider it as a part of the model. I cannot ignore it at all. This is where we have to understand different kinds of methods that are involved in terms of modeling seasonality. And one major method that I am bringing in to handle the seasonality is a regression based model. The same regression based model I want to use with the same data that we have used for the trend. I want to extend it to the seasonality as well and try to work it out. Now, the way we handle the regression analysis is it's one of the most important techniques for modeling the seasonality. So I have to identify that there are S seasons in a year. Season need not be a summer, winter, etc. Any period. So if I'm talking about months, then there are 12 seasons in a year. If I'm talking of quarters, then there are 4 seasons in a year. If I'm talking of weekly, then there are 52 seasons in a year and so on. So I'm talking of S seasons in a year. So if there are S seasons in a year, we say that we will create S minus 1 seasonal dummy variables. Right? So we will create S minus 1 seasonal dummy variables. And the dummy variable will have only a value of 1 or 0, which indicates whether we are in that particular season or not. So if I am talking of 4 quarters, we will create 3 dummy variables. Let's say Q1, Q2, Q3. These are the 3 dummy variables that I am creating. I will not create Q4 because I will leave it as a part of the default. Now what we say is, so let's say here the month is January 2010. So because it comes under Q1, this will be 1, all others will be 0. Let's say I am talking about June 2010. Because it comes under the second quarter, this one would be 1, all others will be 0. Or if I am talking about August 2010, this one would be 1, all others would be 0. And if I'm talking about December 2010, all the three will be 0. So that's how we differentiate the 4 quarters when I'm using this kind of a mechanism to handle my seasonal variables. So I will create Q1, Q2, Q3 as the three seasonal dummy variables, and after that I'll go ahead with the modeling the usual way itself. So this is the dummy variable DIT, which will have values 1 and 0, and it will have s minus 1 dummy variables. Right, I would include s minus 1 dummy variables, not yes, I'll include s minus 1 dummy variables, and remaining and each one will have a different coefficient altogether. That's how the regression model comes into picture. And I can integrate this with the trend as well. So here if you see, so we are including the trend part. Along with that, we are considering the various dummy variables created and their coefficients separately. So we can include the trend part as well as the seasonality part into one single equation itself. So the coefficients on the various seasonal dummies. Now when I'm ignoring the fourth, when I have 4 seasons, I have created only 3 dummies. What we are saying is the fourth dummy is taken care by the intercept itself. So when we are talking of these three, intercept plus the coefficient of this, intercept plus the coefficient of the second one, intercept plus the coefficient of the third one. So this is where I will get the seasonal increase or decrease relative to the omitted season. If I am ignoring the season 4 or Q4, then when I am talking of Q1, it is Q4 with respect to Q4, what is the increase or decrease of Q1? Similarly, what is the increase or decrease of Q2 with respect to Q4, and so on. So the idea of seasonality can very well be extended to allow for more and more general calendar effects. It need not be just 4 quarters. So here in the data, if I have to bring that aspect into this, so let me bring in 4. So I'll say Q1. If at all I'm talking about data which is in January, February or March, then I'm looking at it as Q1. So I'll say if month of this one is greater than or equal to 1, and not probably I'll say I'll put and. If and of month of this greater than or equal to 1, comma, month of this less than or equal to 3, then I will set this particular value as 1, otherwise I'll set it as 0, which means it belongs to the Q1. So wherever you have Q1, it will become 1, in and all the other cases it becomes 0. This same formula I'll copy and I'll change some of the internal stuff here. So when I'm saying Q2, it's greater than or equal to 4 and less than or equal to 6. So this is where I'll set the Q2. So for April, May, June, it's coming out as 1, and for all the other months, it's coming out as 0. Similarly, in case of Q3, I will set it as greater than or equal to 7 and less than or equal to 9. So this is how the Q3 is coming into picture. So I have 3 new variables because I am talking about 4 seasons. So corresponding to S seasons, we have S minus 1 variables. So that is one way we can include the seasonality, that's the general seasonality. But much more than that, we have 2 other definitions of seasonality. One is called as the holiday variation. So especially when some holiday dates are changing over time, let's say the season of Diwali. In some periods, in some years, Diwali comes in October, whereas in some periods, Diwali comes in November. So depending on in which season Diwali is falling, I may be setting. I may feel that the sales could be different for the companies depending on which season the particular festival is falling. In which month the festival is falling, I may have a different assessment of the seasonality altogether. Or probably I can think of the season during which the results are declared, annual results. In some cases, the annual results might be declared during June, which will fall under Q2. And in some cases, they may, I mean, I'm not talking about financial quarters here, I'm talking about the calendar based quarters. In some cases, they may declare their results in July or August, in which case it falls under Q3. So our assessment also sometimes changes depending on the periods in which each of these months are going to fall. So if I want to capture that kind of a variation, we are talking of a holiday variation, and whatever the holidays I want to consider, I can treat each one of them as again a different dummy variable. Right? In each of the years, if I know the dates of Diwali, then I can very well put 1 in those months where Diwali has come, 0 in those months where Diwali did not come. So there will be only 1 month in a year where Diwali has come, and depending on the date, I would track that particular month to be 1 and the other month to be 0. So even then I am creating one more dummy variable to handle the holiday variation. And sometimes I may even have a trading day variation, especially not for this purpose, but let's say if I want to estimate a trading volume or something, then I can look at the trading day variation also, which says how many trading days are there in that particular year. So there could be a few months which are having 19 trading days, few months with 20 trading, 21 trading, 22 trading, 23 trading days. Then I'll create again a dummy variable. Okay, 19 trading days, 20 trading days, 21 trading days, 22 trading days. Again, each one of these values would be either 1 or 0 depending on whether we have. So if this is the kind of a representation, then I say this particular month is having 19 trading days. If this is the representation, I say this particular month has 21 trading days. And if this is the representation, then I may say that this month will have 23 trading days because all of the 19, 20, 21, 22 are 0. So wherever there is a requirement of going with more number of trading days like that, even the trading day variation I can very well bring in. For some of the observations it is very much required for me, especially in terms of let's say why only trading days? We are talking of business days, working days. Right, the more number of working days are there, the sales, if I have to model the total sales, the sales could be much higher if there are more number of business days compared to the periods where there are lesser number of business days. So these are some of the things. If I want to bring them up as a part of my model, it's better that I consider different dummy variables even to incorporate the number of trading days in that particular period as well. So that's how the overall model gets built, and based on this I can very well again create. So here I want to use a linear trend along with this seasonality to really understand. So what I'll do is, for time being, I will hide all these things. So which will leave me with this being my variable to be predicted, and because I am going with the linear trend along with the seasonality, I'll consider these 4 columns itself. So let me hide even this one as well. So now I am going to consider linear trend plus seasonality kind of model. Again the same logic, we need 4 variables out here. So I am considering A as the intercept, then I want B, C, D, E, or probably I can call it as B1, B2, B3, B4. So initially let me have A as 100 and all of them has 1. Based on that, I'll have a predicted value which comes out as A plus B1 times the time factor plus B2 times Q1 plus B3 times Q2 plus B4 times Q3. So this is what is the predicted values across. Based on that, I can find out the error. The error is coming out as the predict actual minus the predicted value. So this forms to be the error, and I'm also talking about an error squared which comes out as this particular value squared. Alright. Now I can find out the total squared error. The total squared error is coming out to be this much, and I would like to change these variables so that this total squared error will be the minimum most. So I'll use solver for this purpose, where I am trying to assess or minimize this particular value. I want to minimize this particular value, changing these constraints. These are the values that I want to change, all else remaining the same. All the model is working out in this way, right? 111121.13. The model has come out like this. If I have to include the seasonality, the model came out as 1121.13 plus 138.42 times the time, and you have 0.9598 times 1 if it is Q1, and we are having plus 1.00 times 1 if it is Q2, plus 1.05 times 1 if it is Q3, and so on. So this is what is the total error that I have got in the process. Right, this is what is the total error that I have got in the process. Now what we are talking of is this is the total error, and as we have discussed earlier, I can very well find out the R squared, right? The R squared will come out as, I also need to consider what has been the total error earlier. Let me unhide it. What is the total squared error earlier? Oh, I have put these things out here. So let me just change the names from here. Let me include one more column here. Let's unhide this. Right, let me insert a few new columns out here, and let me copy or cut this stuff from here to here. Then I can very well, okay, now here this is the total squared error that I am getting. Once I got my total squared error, I can very well get into the predicted value for December 16 using this. Right, I'm going ahead with the predicted value for December 2016, which comes out as A plus B1 times the time. Time is 192 plus B2 times, now this is not the first quarter, so I'm multiplying it with 0. B3 times, even it's not the second quarter, multiplying it with 0. B4 times, it is the first, it's not the third quarter as well, so I'm multiplying it with 0. So based on this, I'm getting the predicted value as 27,697 going with this model. And I can very well find out the error. This definitions and all we have found out using our in the trend series as well. I'm finding out the error sigma, which is coming out as the standard deviation associated with the error term. The standard deviation is in this also is coming out to 2323. Here also it is 2323. So I don't see there is much of an improvement going ahead with linear trend plus seasonality. Looks like the linear trend is having the least amount of error. But anyway, if I am going with this and if I want to go ahead with the lower interval, which is coming out as the predicted value minus 1.96 times the sigma, assuming the error is following a normal distribution, and upper sigma or upper interval is coming out as the predicted value plus 1.96 times the error sigma. So as per this, the value can lie anywhere between 23,144 and 32,252. But quickly I can also calculate the mean squared error, which works out as the total squared error divided by 191, giving me 5.369 million. R squared also I could compute for this model, which is working out as 1 minus I require for R squared, I require total sum of squares, which I can directly take it as this because the data is exactly the same. The total sum of squares is going to be the same. Based on this, I want to compute my R squared, which works out as 1 minus of mean squared error divided by the total sum of squares, working out a mean squared error. R squared is working out as 1 minus total squared, total sum of square, total squared error divided by the total sum of squares. So resulting in 91.55%. And I could also look at the other measures which we have done earlier, where I could look at S squared, which is nothing but the means, when you are looking at S squared, I am looking at the total squared error divided by T minus K. I have to adjust it for the degrees of freedom. Now I have 5 independent variables. A, B1, B2, B3, B4. Oh, I have 4 of them, B1, B2, B3, B4. So T minus 4 is going to be the scenario. 191 minus 4, 187 will be my S squared value. Looks like it's much higher compared to the S squared value that I have got in linear trend. So even with this, the linear trend is a much better model. I can look at adjusted R squared. The adjusted R squared as per this model is coming out as, if you look at the adjusted R squared which we have computed earlier, 1 minus S squared divided by the total sum of squares divided by n minus 1 or t minus 1. So this works out as 1 minus of S squared divided by the total sum of squares divided by 190 t minus 1. So the adjusted R squared is coming out to 91.42%, which is lesser than the 91.55% which we have got for exclusive linear model. So even based on the adjusted R squared, it can be seen that there is no seasonality in the data, only a linear trend is sufficient. Even we can go with EIC as well. AIC, Akaike information criteria, which says I will multiply the mean squared error, I'll multiply it with e to the power of 2k by t. 2k K is 4 here. So 2K by T is 8 divided by 191. T is 191 observations altogether. So AIC is giving me a 5.59 million values, whereas here it is 5.42 million. Again, this is much lesser. AIC is again a measure of error which is much lesser in a linear model compared to a linear trend plus seasonality model. So even going with the AIC, it looks like the linear model is much more appropriate for this data. And even if I am using the Schwartz information criteria, which goes with t to the power of k by t multiplied by mean squared error. So I am taking the mean squared error multiplied by t, 191 to the power of k by t. K is 4, 4 by 191. So SIC has gone quite heavier, 5.99 million, whereas the linear trend model is having an SIC of only 5.51 million. So going with all these measures, it looks like for this example, the linear trend is more appropriate than a combination of linear trend plus seasonality. So we can very well ignore the seasonality part as a part of this model, and I can very safely assume that in this data there is no question of seasonality coming up at all. So that's how we can model the seasonality along with the trend part by considering the regression part of it. And once I have that information, I can go ahead in terms of doing a forecast also, which we have already done. We have looked at the forecast for the next period. If I have to include the seasonality, this is the forecast for the next period. So whatever is known at time t, only those are considered. So this part is not known at time t, so we'll take it as 0. We know the time period. We know whether it falls into a first quarter or not. We know if there is some kind of a holiday variation associated with it or not, or even if this number of trading days variation is required. I will know whether I should consider it as 1 or 0, but only the error term I will not have any kind of an idea. So I will take it as 0, and I would try to include these parameters that I am getting by the regression model as the coefficient for doing the prediction. And we have already looked at the 95% interval, looking at 1.96 times the sigma, because we assume that the error terms after the regression model are normally distributed. And once they are normally distributed, I am looking at the 95% confidence interval of that error term by taking it as plus or minus 1.96 times the standard deviation. And if I want the density forecast along with the lower interval and the upper interval, I take the predicted value and I'll take the 1.96 times sigma on the lower side to get the lower interval, 1.96 times the sigma on the upper side to get the upper interval. So that's how I can create the forecasts as well using the seasonality component in the data. So this is what I wanted to cover as a part of this session. I hope you got a good amount of understanding on how you can blend the seasonality in as well as trend into the model by looking at the data, by creating linear exponential kind of trends and adding it with the seasonality part. How do you really create your regression analysis models to model the seasonality? And based on the best possible model, how do you go ahead in terms of creating the forecasts as well? If you have any further queries regarding the same, you can very well get in touch with me by giving me a call on the number that I have given below, or you can even send in an email at the email address that I have provided. Thanks a lot for listening to this session. Thank you very much.